The exploration of Venus represents one of humanity's most ambitious endeavors, with particular intrigue surrounding the possibility of life in its extreme environment. Throughout the 1960s and 1970s, the Soviet Union's Venera program pushed the boundaries of space exploration by landing probes on Venus, penetrating its dense atmosphere, and collecting invaluable data from its surface. These missions delivered the first-ever images of Venus's landscape and provided direct measurements of its temperature, atmospheric composition, and pressure. These findings transformed our understanding of Venus, painting a picture of a planet vastly different from Earth, yet with enough enigmatic qualities to keep the scientific community intrigued for decades. The Venera probes revealed Venus as a world of extremes, with surface temperatures reaching 465 degrees Celsius and pressures over 90 times that of Earth's sea level. The surface is littered with volcanic plains and towering mountains, while its thick, yellowish atmosphere is composed predominantly of carbon dioxide with clouds of sulfuric acid droplets. Early interpretations of this data dashed hopes for life on Venus, as these conditions seemed utterly inhospitable to any known biological organisms. Despite these challenges, Venus continues to captivate scientists, not only as a cautionary tale of climate change, but also as a potential home for microbial life in an unexpected region: its atmosphere. The detection of phosphine in the upper atmosphere of Venus in 2020 sparked a scientific debate of unprecedented scale, focusing global attention on the enigmatic planet. The announcement, which came from a study led by a team of researchers using data from the James Clerk Maxwell Telescope, JCMT, and the Atacama Large Millimeter Submillimeter Array, ALMA, challenged long-standing assumptions about Venus's habitability. Phosphine is a gas rarely found in nature unless it is produced by industrial processes or biological activity in environments with little to no oxygen. Its presence on Venus, a planet long thought to be utterly inhospitable, raised profound questions about the planet's chemistry and potential for life. Phosphine's molecular structure, made up of one phosphorus atom and 3 hydrogen atoms, is notable for its instability in oxygen-rich environments. On Earth, phosphine is primarily associated with anaerobic ecosystems, such as those found in swamps, marshlands, and even the guts of certain animals. Its production is linked to microbial activity, often in oxygen-deprived environments where organisms thrive under conditions markedly different from those on the planet's surface. The detection of this gas on Venus, particularly in its atmosphere, was unexpected, given that Venus is not known to have the type of ecosystems associated with phosphine production on Earth. The upper atmosphere of Venus, where the gas was detected, presents conditions that are far removed from the planet's searing surface. Roughly 50 to 60 kilometers above the surface, the temperature and pressure are comparable to those found on Earth. However, the atmosphere is dominated by carbon dioxide, with thick clouds of sulfuric acid droplets, creating an extremely acidic environment. Phosphine's survival in such conditions has perplexed scientists, as it is highly reactive and would typically break down in the presence of acidic compounds. Its persistence in the Venusian atmosphere implies either a continuous source of production or an unknown mechanism preserving it against rapid degradation. Following the announcement of phosphine's detection, researchers began examining possible abiotic processes that could explain its presence. Suggestions included volcanic activity, lightning strikes, or chemical interactions involving minerals ejected from Venus's surface. However, these theories faced significant hurdles. Volcanic eruptions, while plausible, would need to occur at an unprecedented scale and frequency to produce the observed levels of phosphine. Similarly, lightning strikes, while known to generate certain compounds, are not sufficient to account for the concentration of phosphine detected. These challenges have left the door open for the possibility that the gas might be linked to a biological origin, albeit under conditions vastly different from those on Earth. The scientific community's response to the detection of phosphine was mixed, reflecting both excitement and skepticism. While some researchers hailed the discovery as a potential breakthrough in the search for extraterrestrial life, Others questioned the reliability of the data. Concerns were raised about the methods used to process the spectral data, with critics pointing to possible errors in calibration or noise in the signal that could have produced a false positive. Subsequent analyses have yielded conflicting results, with some studies failing to replicate the original findings and others confirming the presence of phosphine, but at lower concentrations than initially reported. Amidst the controversy, the detection of phosphine reignited interest in Venus as a target for astrobiological research. Historically overshadowed by Mars and the icy moons of the outer solar system, Venus has often been overlooked in the search for life due to its harsh surface conditions. However, the discovery of phosphine has shifted attention to the planet's atmosphere, where conditions are less extreme. This renewed interest has led to calls for dedicated missions to Venus to study its atmosphere more comprehensively and to determine whether the phosphine signal is genuine, and if so, what might be producing it. The detection of phosphine also raises broader questions about habitability and the adaptability of life. If the gas is indeed being produced by biological processes, it would suggest that life can exist in environments far more hostile than those typically considered habitable. On Earth, extremophiles, organisms that thrive in extreme environments, such as acidic hot springs or deep-sea hydrothermal vents, demonstrate the remarkable resilience of life. If similar organisms exist on Venus, they would need to withstand extreme acidity, limited water availability, and high levels of ultraviolet radiation, pushing the boundaries of what is considered biologically possible. In addition to its implications for biology, the presence of phosphine could provide valuable insights into Venus's atmospheric chemistry. Venus's atmosphere remains poorly understood compared to that of Earth or Mars, and the detection of unexpected compounds like phosphine highlights the need for further exploration. Understanding the processes that sustain phosphine, whether biological or abiotic, could shed light on the planet's chemical cycles, offering clues about its history and evolution. This knowledge, in turn, could inform our understanding of planetary atmospheres more broadly, including those of exoplanets beyond our solar system. The discovery of phosphine has also influenced the direction of future planetary exploration. NASA and other space agencies have announced new missions to Venus, including the Da Vinci Plus and Veritas missions, which aim to investigate the planet's atmosphere and surface in unprecedented detail. These missions will complement observations from Earth-based telescopes, providing data that could help confirm or refute the presence of phosphine. Additionally, the European Space Agency's Envision mission and proposals from other countries, such as India's Chandrayaan-1, underscore the growing interest in Venus as a key target for exploration. While definitive answers about the origins of phosphine on Venus remain elusive, the discovery has already had a profound impact on the scientific community. It has highlighted the importance of re-examining long-standing assumptions about habitability and has underscored the need for continuous innovation in observational techniques. The debates surrounding the detection of phosphine have also demonstrated the self-correcting nature of science, as researchers scrutinize methods and interpretations to ensure that conclusions are robust. The detection of phosphine has also captured the public's imagination, sparking renewed curiosity about Venus and the possibility of life beyond Earth. This widespread interest has revitalized discussions about humanity's role in exploring the solar system and the broader universe. It serves as a reminder of the enduring appeal of space exploration and its potential to uncover answers to some of the most profound questions about life and our place in the cosmos. The detection of phosphine in Venus's atmosphere in 2020 represents a landmark moment in planetary science, offering both tantalizing possibilities and significant challenges. Whether the gas is produced by unknown abiotic processes or by biological activity, its presence highlights the complexity of Venus as a planetary system and underscores the need for further investigation. The discovery has reignited interest in Venus, positioning it as a key focus for future exploration and a critical piece in the puzzle of understanding life's potential beyond Earth. Further supporting this idea is the stability of life's essential building blocks under Venus-like conditions. Recent experiments have demonstrated that certain amino acids, the fundamental components of proteins, can remain stable in environments containing sulfuric acid. In one study, researchers exposed 19 amino acids to sulfuric acid concentrations akin to those in Venus's atmosphere, finding that they remained stable for up to 4 weeks. This discovery suggests that some of the basic ingredients for life could endure in Venus's acidic clouds, bolstering the hypothesis that microbial life might find refuge there. The detection of ammonia in Venus's atmosphere has added another intriguing layer to this narrative. Ammonia could play a key role in creating microenvironments where life might thrive by neutralizing the surrounding sulfuric acid, reducing the acidity to levels more conducive to biological activity. If ammonia is indeed present, it would also imply the existence of a previously unknown chemical or biological process capable of producing it under Venus's harsh conditions. This finding raises questions about the planet's atmospheric chemistry and whether it harbors processes distinct from anything observed on Earth. Despite these promising developments, the scientific community remains cautious. Some researchers propose that the observed phosphine might result from as-yet unknown abiotic chemical processes occurring on Venus, potentially involving the interaction of sunlight with minerals or volcanic gases in the atmosphere. Others have suggested that the phosphine detection could be a false positive, stemming from limitations in the observational data or the methods used to analyze it. These alternative explanations underscore the need for further investigation to confirm or refute the initial findings. Another fascinating, albeit speculative, idea is that Earth microbes could have been inadvertently introduced to Venus during the Soviet Venera missions or other spacecraft flybys. If microbes from Earth somehow survived the journey and adapted to Venus's atmosphere, they could potentially explain the presence of phosphine. However, this scenario remains highly improbable given the extreme conditions of Venus and the technological constraints of past missions. Nonetheless, it highlights the complex interplay between exploration and contamination, emphasizing the importance of planetary protection protocols in future missions. The renewed interest in Venus has spurred plans for new exploratory missions by organizations like NASA, the European Space Agency, ESA, and Roscosmos. NASA's Veritas and Da Vinci Plus missions, set to launch later this decade, aim to study Venus's geological history, atmospheric composition, and potential habitability. Veritas will map the planet's surface in unprecedented detail, while Da Vinci Plus will deploy a descent probe to analyze the atmosphere as it makes its way to the surface. These missions could provide critical data to confirm the presence of phosphine and other potential biosignatures, shedding light on whether Venus's atmosphere might support life. The European Space Agency's Envision mission, scheduled for the early 2030s, will complement these efforts by focusing on Venus's surface and its interaction with the atmosphere. Meanwhile, India's ISRO has also expressed interest in a Venus mission, further underscoring the global importance of unraveling the mysteries of this enigmatic planet. These missions represent a new chapter in Venus exploration, building on the legacy of the Soviet Venera program while leveraging modern technology to address questions that were previously beyond our reach. The implications of finding life or evidence of past habitability on Venus would be profound. It would challenge our understanding of the conditions necessary for life and expand the potential locations where life might exist beyond Earth. Even if life is not found, studying Venus's atmosphere and surface could yield valuable insights into planetary evolution, climate dynamics, and the interplay between geology and atmospheric chemistry. Venus serves as a natural laboratory for understanding runaway greenhouse effects, offering lessons that could inform our approach to addressing climate change on Earth. In addition to its scientific value, the search for life on Venus has broader philosophical and cultural significance. The possibility that life might exist in such an extreme and unexpected environment challenges our assumptions about the uniqueness of Earth and its biosphere. It also underscores the resilience of life and its ability to adapt to a wide range of conditions. These ideas resonate deeply with humanity's enduring quest to understand our place in the cosmos and whether we are alone in the universe. The history of Venus exploration is a testament to humanity's relentless drive to uncover the mysteries of our neighboring planets, fueled by the ambition to understand the cosmos and our place within it. Venus, long referred to as Earth's twin due to its similar size and composition, has captured the imagination of scientists and the public alike. Its thick, reflective atmosphere has veiled its surface from direct observation, making it a tantalizing target for exploration. Over the decades, missions to Venus have revealed a world of extreme conditions and unexpected phenomena, transforming it from a symbol of Earth's celestial sibling into one of the most enigmatic and intriguing planets in our solar system. The journey began in earnest during the Cold War, as the Soviet Union and the United States sought to extend their rivalry into space exploration. The Soviet Union's Venera program, which launched its first mission in the early 1960s, marked a series of significant milestones in the exploration of Venus. Despite early failures, the program eventually achieved groundbreaking successes, including the first-ever landing on Venus's surface by Venera 7 in 1970. The Venera program continued to make history with subsequent missions. Venera 9 in 1975 became the first spacecraft to send back images from the surface of another planet, offering a glimpse of Venus's rocky terrain. These images revealed a landscape shaped by volcanic activity, with basaltic rocks and a lack of visible craters, suggesting that the planet's surface had been geologically active in the recent past. Venera 13 in 1982 further advanced our understanding of Venus by capturing color images and analyzing surface samples. These missions not only demonstrated the resilience of Soviet engineering, but also set the stage for future planetary exploration by showing that it was possible to operate in such an extreme environment, even if only briefly. While the Soviet Union led the way in Venus exploration, the United States also made significant contributions. NASA's Mariner 2, launched in 1962, became the first spacecraft to successfully fly by Venus, providing critical data about its atmosphere and temperature. Later, NASA's Pioneer Venus program in the late 1970s deployed a multi-part mission, including an orbiter and several probes, to study the planet's atmosphere and surface. These missions expanded our knowledge of Venus's atmospheric composition, revealing the predominance of carbon dioxide and the presence of sulfuric acid clouds, which contribute to its intense greenhouse effect. The 1980s and 1990s saw further advancements in Venus exploration, with missions like NASA's Magellan spacecraft, which used radar to map Venus's surface in unprecedented detail. Magellan's radar imaging unveiled a planet dominated by volcanic plains and extensive rift valleys, suggesting a dynamic geological history. It also identified features such as pancake domes and coronae, unique volcanic structures that challenge scientists to rethink their understanding of planetary geology. These findings provided valuable insights into Venus's tectonic activity and internal processes, drawing comparisons and contrasts with Earth. Despite these achievements, interest in Venus waned during the early 21st century as missions focused on other targets, particularly Mars and the icy moons of the outer solar system. However, Venus remained an object of fascination, with intermittent missions such as ESA's Venus Express, launched in 2005, which studied the planet's atmosphere and climate. This mission revealed intriguing details about Venus's super-rotating atmosphere, where winds in the upper atmosphere travel at speeds of up to 360 kilometers per hour, much faster than the planet's slow rotation. In recent years, Venus has re-emerged as a priority for planetary exploration, driven by discoveries that challenge previous assumptions about its habitability. The detection of phosphine in 2020 reignited interest in Venus as a potential host for life, drawing attention to its cloud layers, where temperatures and pressures are more Earth-like. This finding, while controversial, has underscored the need for further exploration to confirm its validity and understand the processes behind it. Venus's atmosphere, long overlooked in the search for extraterrestrial life, is now seen as a promising site for astrobiological studies. The exploration of Venus holds profound implications for planetary science and astrobiology. Understanding Venus's extreme greenhouse effect offers valuable lessons for Earth's climate, highlighting the potential consequences of runaway warming. The study of its geological history could reveal why Venus evolved so differently from Earth, despite their similar sizes and compositions. Moreover, investigating its atmosphere for signs of life or unique chemical processes expands our understanding of habitability, challenging traditional assumptions about the conditions necessary for life. As humanity prepares to return to Venus, the legacy of the Venera program and other pioneering missions serves as a foundation for future discoveries. Each mission has contributed to a deeper understanding of the planet, transforming it from a mysterious twin of Earth into a world with its own unique and compelling story. These endeavors exemplify the power of human curiosity and ingenuity, driving us to explore the unknown and seek answers to some of the most profound questions about our universe. The potential for groundbreaking discoveries on Venus, including the possibility of life, underscores the importance of continued exploration. Venus is not just a scientific target, it is a symbol of humanity's drive to push boundaries and confront challenges in the pursuit of knowledge. As we prepare for the next chapter in Venus exploration, we stand on the cusp of answering questions that could redefine our understanding of life and the cosmos, affirming the enduring relevance of this enigmatic planet. The journey to understand Venus and its potential for life has been shaped by decades of exploration and discovery. The detection of phosphine, the stability of amino acids in acidic environments, and the presence of ammonia in Venus's atmosphere have reignited interest in this inhospitable yet fascinating planet. While definitive evidence of life remains elusive, the scientific and philosophical implications of these findings continue to drive exploration. With upcoming missions promising to deliver unprecedented data, the mysteries of Venus may soon yield their secrets, offering a glimpse into the possibilities of life in the cosmos. We'd love to hear your thoughts on the incredible history and future of Venus exploration. Do you think the upcoming missions will uncover groundbreaking discoveries or even signs of life in the planet's atmosphere? Share your ideas and opinions in the comments below. If you enjoyed this deep dive into the mysteries of Venus, don't forget to like, share, and subscribe for more captivating content. Thanks for watching, and we'll see you next time.